Hello, and welcome to Science with Mr. Morgan. In today's episode, we're going to talk about nuclear chemistry. First up, let's take a look at radiation. But before we can say what radiation is, we have to talk about radioactivity, which is just the ability of an atom to emit charged particles and energy from its nucleus. Now, that being said, radiation is the charged particles and energy that are emitted from the nucleus. If an isotope of an element is radioactive and emits radiation, it is known as a radioisotope. And these are, as I alluded to, isotopes of elements that are radioactive. A popular example that we're going to spend a little bit of time talking about and touching on is carbon-14. Now, the nuclei of radioisotopes are unstable, which leads to constant decay and emission of radiation. Remember how I mentioned carbon-14 a few seconds ago and said we're going to talk about it? Carbon is an element that has non-radioactive isotopes as well as radioisotopes. In elements that have more than 83 protons, all of the isotopes are radioactive, which is different from carbon. Now, like I said, carbon can have radioisotopes. There's carbon everywhere. We're constantly being exposed to what is known as background radiation. And this background radiation is a very low level of radiation that occurs naturally in the environment. And while background radiation at low levels is not inherently dangerous to us, long-term or high-dose exposure to radiation can harm living things and even damage non-living materials, such as metals. This, along with the fact that radiation can't be detected with our senses, is what makes radiation so dangerous. Since it can't be detected with our senses, we use equipment such as Geiger counters and dosimeters to measure the radiation levels around us. Now, even though radiation is dangerous, it can have very important uses as well, such as diagnosing and treating cancer. Now, earlier I mentioned how radioactive isotopes emit radioactive particles from the nucleus. This process is known as radioactive decay. By definition, it is the process where the unstable nuclei of radioactive atoms become stable by emitting charged particles and energy. Similar to other things in science, there are multiple types of radioactive decay. Alpha decay is the first type that we're going to talk about. And this is where energy and alpha particles are emitted by a nucleus that is unstable from too many protons. So what is an alpha particle? It's a particle that's made up of 2 protons and 2 neutrons and is the least dangerous type of radioactive particle. Beta decay is the second type we're going to look at today. It is where energy and beta particles are emitted by a nucleus that has too many or too few neutrons relative to the number of protons it has. So what is a beta particle then? Well, it's either from an electron, which is known as beta minus decay, or a positron, which is beta plus decay. Beta minus decay is where a neutron releases a proton and an electron from the nucleus, whereas beta plus decay is where a neutron and a positron are released from the nucleus. Beta decay is harmful to living things. And the last type that we're going to talk about today is gamma decay. It is where a packet of energy, aka gamma particles, are emitted from a nucleus. Gamma particles are carried on gamma rays, and remember, these are the most energetic of all electromagnetic waves, which in turn makes gamma decay the most dangerous type that we're going to cover. Gamma radiation, remember, if you follow the Marvel Universe at all, is also what caused the Hulk to become the Hulk. But that's enough about radioactive decay. Let's switch our conversation to half-life instead. Now, when I mention half-life, am I referring to the video game franchise? Nah. I'm referring to the constant rate that a radioisotope decays and changes to a different element. Half-life is the length of time that it takes for half of a given amount of the radioisotope to decay. Each time this occurs, it gets cut in half, hence the name half-life. This is not something that is constant across all elements, though. Different radioisotopes may vary greatly in their rate of decay and their half-life. The more unstable the nuclei of those radiotypes are, the faster the decay is. This half-life is known for many radioisotopes, which allows it to be used for something known as radioactive dating. Now, is this where a gamma particle takes a beta particle out to dinner? Nope, at least not what I'm referring to in this moment. Radioactive dating is the process of estimating the age of a specimen using the remaining amount of radioisotope it contains and the radioisotope's known rate of decay, aka the half-life. Radioisotopes with longer half-lives are used to date older specimens, while radioisotopes with shorter half-lives are used to date younger ones. Carbon-14 dating, that radioisotope I keep mentioning, is used to date specimens younger than approximately 60,000 years old. With this date range, carbon-14 is commonly used to date fossils of living things and even human artifacts. Moving on from radioactive dating, though, we're going to now look at nuclear fission and nuclear fusion. Nuclear fission is the splitting of the nucleus of an atom into two smaller nuclei. This ends up releasing a great deal of energy from a very small amount of matter. It begins when the nucleus of a radioactive atom gains a neutron. And when one fission reaction starts, chain reactions end up starting, which is known as uncontrolled nuclear fission. Neutrons that are produced in one reaction cause other reactions, which cause other reactions, which cause other reactions, which cause other reactions, which cause other reactions, and so on. Now, energy released by nuclear fission is what is used to produce electrical energy in nuclear power plants. On one hand, nuclear fission is good because it doesn't produce air pollution. However, it does pose the risk of accidents that release harmful radiation. And this is what occurred at the Chernobyl power plant in Ukraine in 1986. Aside from nuclear fission, there is also nuclear fusion. And this is where two or more small nuclei combine to form a single larger nucleus, a neutron, and a large amount of energy. Nuclear fusion of hydrogen to form helium occurs naturally in the sun as well as other stars and is what powers them. Now, as you might suspect from being in the sun, this process takes place only at extremely high temperatures. Scientists want to recreate controlled nuclear fusion, or rather create it on Earth, in order to produce safer nuclear power. However, the temperatures required for this to happen are not readily feasible to accomplish at this time. Now, I mentioned safer nuclear power. It's safer because nuclear fusion involves only harmless, plentiful elements, but again, it requires extremely high temperatures. And that brings us to the end of today's lesson. Until next time.